Okay guys, let's take a look at today's lesson. We're going to look at geometric sequences. This is 13.3. Let's get the formulas. Let's talk about the formulas first and then we'll do some examples. Just as with arithmetic sequences, the nth term is just a vocabulary word that means the formula that generates them. So this would be the nth term formula, where a sub 1 is my first term and r is my common ratio. So that's just the standard formula. Now geometric sequences don't have to look like this. They could have like r to the n or r to the n plus 1. You know, you'll see them in different versions. But this particular version is the standard one for writing them in PreCal. Okay, that's what we will look at in PreCal. So the common ratio, if you remember from last year, that's basically what number are we constantly multiplying by or dividing by to get the next term. That's the common ratio. Alright, so now if we want to find a partial sum of a geometric sequence, we have a formula just like we did in arithmetic. So our s sub n is going to equal our first term, and then we have the 1 minus our r, which is our common ratio, to the n over 1 minus r. Alright, and the last formula, this one only applies to infinite geometric series. Okay, and so we can tell if a series will converge. This is called converging. We can tell if a series converged if its absolute value of r is less than 1. That is the only time that we are allowed to use this formula. We are not allowed to use it in any other circumstance, only if the absolute value of our common ratio is less than 1. Okay, that means that the geometric series will converge. In other words, it will head towards a particular number. It will add up to one particular number. So that's what we're looking for to use this formula. So this formula is pretty important. You actually will use it in calculus. We do infinite geometric series in calculus, and so, well, in BC calculus. So this is my sum. A sub 1 is my first term, and 1 minus r again is our common ratio. Okay, and that is our infinite geometric series formula, only allowed to be used when absolute value of r is less than 1. Okay, how are we doing? Okay. All right, I'm going to try something different. Do that. And keep the writing. So if something horrible happens, the writing is still there. Okay, we'll try. Okay, so let's do some examples. My first example is find the 8th term of the geometric sequence. Basically, we have 3, 5, 45. A lot of you are really good with numbers in your head. You probably already know what this is. Let me talk to you about the technique to use if it's more difficult than this. What you would do is you would take like the second term and divide it by the first term. This is how you find the common ratio. Just a reminder from last year. You take the second term, divide it by the first term, get that ratio. That's a 3. Then just to double check to make sure it is geometric, you would take the third term and divide it by the second term, and that would give you 3. And then you would know that it's geometric. So that's just a reminder on how to find the common ratio. So we know our a sub 1 is 5, and we know our r is 3. So we just use the formula that we will have memorized on to the nth term. And we do a sub n equals 5, which is our first term. Common ratio is 3 to the n minus 1. And that's just the standard form that we use. Now, resist the temptation to multiply the 5 times the 3, because that would be breaking order of operations if you did that. I have some students that really, really want to do that and think that it makes it more simple, but it really actually ruins it. So don't do that. You have to do exponents first before you multiply by the 5. Okay? Yes. Because this exponent applies only to the 3. It applies to what it's touching. It doesn't apply to the 5. Okay? So that's why it's right outside there. Okay? All right. So that is our formula. Now to find the 8th term. We just sub an 8 in, so a sub 8 equals 5 times 3 8 minus 1. We do our computations and get 10,935. And that is our 8th term. Yes. I don't know about you, but I'm not really fond of multiplying 3 to the 7th. Maybe some of you like doing that, but I really don't like doing that. So yes, on one like this, that's really gigantic, you're going to have a calculator. We may give you some that are smaller, that are more easy to do. You know, on paper, those you would be able to do yourself, but something this large, you would have a calculator for. Okay, we okay? All right. Let's look at our next example. Number 2. Number 2 says the third term of a geometric sequence is 63/4, and the sixth term is 1,701 over 32. Find the fifth. Okay. Unlike the little formula that we had yesterday where we could just put the terms on, subtract the terms on top, and on the bottom we would subtract the term numbers and get the common difference. We really don't have a fancy little formula like that. We have to do it more like solving a system the second way that I showed you yesterday. So and what I want to always do is I want to always put the larger term, I want to work with the larger term first. So what I'm going to do is I'm going to set up the standard equation. I'm going to make 1701 over 32 my answer to the standard equation. I don't know my first term. I don't know my r, but I do know that it would be to the 6 minus 1. And you could go ahead and write 5 there. I just wanted you to see how I got that. Okay, and then the other equation, my answer to that one is 63/4. And I don't know the first term, I don't know r, but I do know that this is the third term, so it will be 3 minus 1. Now, the quickest way to do this, which is what I'm going to show you, is to divide the two equations. Now, I know that's not a normal thing that we do. We don't normally divide equations. We add them, we subtract them, but it is perfectly allowable as long as you have the equal signs lined up. So I'm just going to divide these two, and I would have a calculator. So I would put these numbers in my calculator and I would divide them, and I would end up with 27/8 after I put those numbers in my calculator. The a sub 1s, they cancel out, don't they? They're gone. So basically what I have left is r to the 5th over r to the 2nd. And we know how to combine those together to be 1r, right? If we're dividing, we subtract the exponent. So I would have, 5 minus 2 is 3. Bless you. And so then I would cube root both sides. And I get r equals, 3/2. So that's my r value. A little bit more complicated than yesterday, but not too bad. We just put one equation over the other and divide them. It's pretty quick. The a's are always, well, in this kind of situation, the a's will go away. So we have the r. Now we just need to find our first term. So, sub back into one of them, whichever one you like. I kind of like smaller numbers better, so I would probably pick this one. So 63/4 equals a sub 1. My r is 3/2. And this was to the 2nd. So then I solve for that. You could certainly, use your calculator. A sub 1 would be 7. And isn't that amazing? Those pretty numbers come out of that mess. So that's my formula. Now I just need the 5th term. So a sub 5 is going to equal my first term times 3/2 to the, let's see, we want 5 minus 1, so to the 4th. So I work that out and I get 567/16. And it would be best to leave it in accurate form. If you did a decimal, I don't know that this comes out evenly. I can't tell by my work, but you really want to keep in mind that if you can give an accurate answer, that's what you want to give. You would prefer to give an accurate answer over an estimate. Okay, so we would just leave it like that. That would be our fifth term. Questions? Okay. Let's look at number 3. Okay, number 3 says find the sum of the first 5 terms of the geometric sequence. Alright, so we just want the first 5 terms. That's great. Let's see if we have everything for our formula. Our formula that we want to use is this S sub n equals a times 1 minus r to the n over 1 minus r. Okay, and we have our a, that's our first term, got that. R, we can figure that out, right? Because I just want to take this one divided by that one, that one divided by that one. And basically I'm going to get 0.7. And we know how many terms. It says 5, so we're pretty much set to go. We don't really have to find very much other than the common ratio. So S sub 5 equals 1 times 1 minus 0.7 to the 5th over 1 minus 0.7. And you would have your calculator and you would type that in. That's not going to come out very pretty. But we always want to go to at least the thousandths. If you want to go past the thousandths, that's just fine. That is our standard for calculus. So that's what we work on all throughout. That's why we do thousandths, is because we need, they will not, if on the test this was the answer and you wrote 2.77, you wouldn't get that point. That's how picky they are. You wouldn't get any credit for it whatsoever. So you've got to be sure to go to the thousandths unless it says otherwise. All right, number 4 wants us to find that summation. It's infinite. Now, our calculators, we can't put infinity in it, right? We don't have an infinity button. So we've got to think about this. Is this geometric? It's not written very nicely. Let's rewrite it. Let's see if we can rewrite it and make it look more like a geometric. Okay, so we have the n equals 0 to infinity. That 2 isn't affected by the exponent, is it? I'm going to pull it out and make it right there in front. I'm just going to do that. Then I'm going to write 1/5 to the n. Now, is that the same thing that I started with? Yeah, it's the same thing. So now we can see that it is geometric, and our common ratio is 1/2. So does this meet the criteria to use the formula for an infinite geometric series? Yes. Oh, excuse me, 1/5. It's 1/5. Yes, it does. So we are allowed to use that formula, and that's what we would use here. We would say sum equals, our formula is A is, that would be a 2 over 1 minus R, which is 1/5. You really wouldn't need a calculator for this little guy, but when you work that through, you would end up with 5/2. And that's our sum for that. Okay? All right. Let's look at number 5. Now, for some reason, some students just think this is the easiest thing in the world, and some students seem to never get it. I don't really know what it is about it. So kind of stick with me, and let's make sure we're okay. What we're going to do is we're going to take a repeating decimal, or a number and a repeating decimal that's attached, and we're going to write it as a series. We're going to write it as an infinite series. So what I do is, first of all, I determine which part is repeating. That's the 5/1, isn't it? The 5/1, this is the part right here that's repeating. The part that is not repeating doesn't get to be in the formula part, okay? He just gets to hang out, have fun, when we're all done, then he gets to add back in. Okay, the 2.3 is just, it's going to stay there. It's going to be 2.3. Okay, it's not, doesn't get to partake in the fun of the repeating part. So now, basically what I'm doing is really like you did in elementary school. I don't know if you remember when you expanded those numbers. You would expand a number and you would turn this into 2.3 plus 0.051 plus point. See, I'm just putting it in its place, in its, the place that it belongs. So then it's 0.123000051 plus point, and we always need, this is a standard, it's a standard in calculus, we need 3 terms to constitute the pattern. You need to write 3 terms, and this first one doesn't count. Okay, that first one is just like an extra guy hanging out. These, I need 3 of these to constitute a pattern. So 1, 2, 3, 4. So 1, 2, 3, 4, 5, 5, 1 plus dot dot dot. It keeps going on. I don't know about you, but I think 3 is probably enough. I don't want to keep writing those out. So that's my series. Now that's it in decimal form. What we really are going for is fraction form. And those of you that can go straight to a fraction don't need to write this first part. Okay, you can just go straight to a fraction for me. So this would be 23 tenths. This would be 51 thousandths. 51 Okay. That's what we're going for. Alright. Okay. I lost a 0 along the way. There we go. Now we're good. I don't really like all those. That really bothers me. Yes, I'm strange. So this is 100,000. This is 10 million. Alright. So this step right here is not necessary unless you really need it to translate into fractions. We need it to be in a fraction form. Alright, so that's my series. That's great. I'm done writing my series. Part 2 says find the sum of the infinite series. Okay. Well, it's, we hope it's geometric, and it is. How do we find out if it's geometric? We take the second term divided by the first term. Again, this is like an extra guy. I'm not including him in the pattern right now. He's just hanging out. So 51 over 100,000 divided by 51 over 1,000. Do that in your calculator. And you're going to get 1 over 100. So my R is going to be 1 over 100. And I found that by simply dividing, this one divided by this one, or this one divided by that one, whichever one you want to do. My A sub 1 for the repeating part is 51 over 1,000. So to find the sum, I use that cool sum formula. Sum equals first term, which is 51 over 1,000 over 1 minus R. Now, let's talk about this, because this you should be able to do without a calculator. The numbers are big, but it's not that hard. And I want to make sure you understand we can do this without a calculator, and you're probably going to have to. How can I tell what this is being multiplied by without dividing, without going through a lot of difficult computations? Yeah, but just the bottoms, right? The number of zeros that I have. I'm going from 3 zeros to 5 zeros. I have an increase in 2, so that's at 1 over 100. Okay, so it should not be difficult to find R. And also, we can do this by hand. So let's just do that. So that's 51 over 1,000 And 100 over 100 minus 1 over 100 is going to be 99 over 100. So that's the same thing as 51 over 1,000 times 100 over 99. Let's see how we can get the 100 and the 1,000 to cancel, or parts of it. So we're left with 51 over 990. Alright, now that part, the 51 over 990, that is my repeating part. Is that the whole thing? No. Remember that little guy we left out to the side because he couldn't join the party because he's not the repeating part, but we can't ignore him. It really, and I'll just move it down here. So we have to do the 23 over 10 plus 51 over 990. Okay? And that is 388 over 165. And that is my final answer. Okay, so you can see why some students are like, this is the easiest thing in the world, and some students are like, oh my gosh, what did she just do? Okay? Questions? Alright. Last problems, the last type of problems. Okay, for each infinite geometric series, find the interval of convergence and the sum expressed in terms of x. Okay, so what you don't know, which is absolutely so cool, is that these are called power series. Okay, and we do power series in BC Calc. We work with power series. What makes it a power series is it has an x in it. Okay, it has x in it, makes it a power series. So we're actually doing a little bit of what we do in calculus, just in a PreCal way. We want to find the interval of convergence, which is a big deal next year, and we want to find the sum expressed in terms of x. So, all a big deal. So let's do that. So the interval of convergence. Well, what was our rule for the interval of convergence? We needed our absolute value of r to be less than 1 to converge, right? That's our rule. So first of all, I have to find r. And I do that by, like we did just before, divide. This one divided by that one, or this divided by that. So it's either, let's do scratch work up here. So it's either negative x minus 2 divided by 1, which gives me negative x minus 2. Or it's x minus 2 squared divided by negative x minus 2. And see, that simplifies, and I'm left with negative x minus 2. Okay, so that's my scratch work for finding my common ratio. You just do it by dividing. So that's our r. R equals negative x minus 2. Now, what we want to do is we want to force it. We want the absolute value of r to be less than 1. That's what we're looking for, is the absolute value of r to be less than 1. Okay, now resist the temptation to just start crossing out negatives. That's not the way that works. All right, what we need to do is we need to translate it into an inequality without an absolute value bar. In fact, if you want to go ahead and distribute the negative, you are welcome to. It'd be negative x plus 2. And let's just do that on the next step. Do you remember this would be a less than or an and? Remember how we open that up? That goes in the middle, the negative x plus 2, and it's surrounded by 1 and negative 1. Remember that from long ago? So we're going to solve for x, and I'm actually going to do that all together. I'm going to subtract 2 from both sides. So I have negative x is less than 1 minus 2 is a negative 1. Negative 1 minus 2 is a negative 3. Then I have the negative x issue. I don't want to confuse us, so why don't we treat these separate now? Because I don't want to confuse what we're doing. So we're going to solve this piece, and then we're going to solve this piece. And we're going to do it in two pieces. So I have negative x is less than negative 1. And you can think of, remember the rule about dividing by negative, what happens to the inequality? It flips. Or you can just add that one over and add that one over, however you want to think about it. So x is going to be greater than 1. And on this side, we have negative 3 less than negative x. And again, we're going to have x is less than 3. Okay. So x is smaller than 3 but bigger than 1. That's written kind of weird, isn't it? We need to pretty that up. Basically, x is between 1 and 3. Would we agree with that? Between 1 and 3. That is called my interval of convergence. That's really important. Interval of convergence. And then we get to do other fun stuff with it next year. We actually aren't done. We're done for us, but not in the future. So now we want the sum. We know that if I place an x in this power series that is between 1 and 3, it's going to converge. That's what this tells me. It's going to add up to be one particular number. And so what we want to do is we want to get a formula for that. We're going to get a formula for the sum, so that if I pick an x between 1 and 3, I can find out what the sum is by using my formula. All right, so let's do that. So our formula is S equals, we have our a sub 1 term, which is 1, over 1 minus r, and r is a, however we want to write, negative x minus 2 is how I have it written right here. So that simplifies to be 1 over x minus 1 after I pretty it up. So that's what my sum formula is, 1 over x minus 1. I can, if I have an x value between 1 and 3, I can sub it in this formula and find out what the actual sum is. Okay? Are we okay? Last one. A little bit more difficult. Just a little. Oh, can't get that up farther. Alright, so I'm going to write up a little. We're not going to do this one again. I'm going to do number 7, but I'm going to write up higher so that y'all can see it. Same strategy. We want to find the interval of convergence. We need the r first. So on my scratch work over here, negative x to the 4th over 6 divided by x squared over 3. I flip it, negative x to the 4th over 6 times 3 over x squared. And I simplify, and I get negative x squared over 2. That's my r. I hope everyone's comfortable enough. I don't need to show you the other 3, the third one divided by the second one. That's our r. So r is negative x squared over 2. We want to find the interval of convergence. So we do our rule. Absolute value of r has to be less than 1. Okay, we write it into our, take the absolute value bars off. We have to translate it. So negative 1 less than negative x squared over 2 less than 1. At this point, I could multiply both sides by 2. Let's just do that. So negative 2 less than negative x squared less than 2. Now, resist the temptation to get rid of the negatives and start square rooting stuff. We cannot, I know I've talked about it before, probably a gazillion times. Maybe you don't even remember. I don't know. You are not allowed to do those kinds of computations with a squared or a square root or anything like that. You have to do sign analysis. That's your choice. That's all you got. So let's, we're going to split it into two pieces. I'm going to solve this piece first, and then we'll look at that one. Actually, we won't even have to look at that one because this first one's going to take care of everything. So I have negative x squared less than 2. I need to shove everything to one side. And so we get, well, first of all, negative x squared is less than 2. That's always going to be true, isn't it? That one's not going to help us. We need to do the other one. So negative 2 less than negative x squared. So again, move everything to one side. I'm going to move it over there. X squared minus 2 less than 0. We factor. We get negative root 2 and positive root 2. I'm not showing the factoring part. Do I need to, or are we okay? I don't think I need to show the factoring part. Then I check my signs, and my signs turn out to be plus, minus, plus. Which section do I want to keep? The negative one, right? Because we want to be less than 0. So this is my interval of convergence from negative root 2 to root 2. And my S, again, we use our formula. S equals first term, which is x squared over 3 divided by 1 minus r, which is a negative x squared over 2. And just for time's sake, no, I probably need to show this. So this turns into x squared over 3 over, this is 1 plus that. I need to get that to be one thing, so I need to have a common denominator. I'll make this 2 over 2. So this is going to be 2 plus x squared over 2. Everybody okay with that? Just common denominator. Now I flip it upside down. So I have x squared over 3 times 2 over 2 plus x squared. And I pretty much am stuck in the water. I can't really do anything. So it's x squared over 3 times 2 plus x squared. Bless you. There's no fixing that. Now, what is this going to be used for? What's the purpose? What can we use this for? If we had an x value that was between negative root 2 and root 2, we could sub it in and see what the sum was. Okay? How's that? That's probably the hardest one right there. Okay?